As we have mentioned in the previous lecture, the Lax-Milgram-Friedrichs theorem, which was used in establishing the existence and uniqueness of weak solutions for linear impulsive ODEs, the proof of that relies on the Hahn-Banach theorem. So before we state and prove this Hahn-Banach theorem, let us consider the following situation. So suppose we have a Hilbert space, let's say X, given an element X in the Hilbert space, the inner product of Y and X is 0 if and only if, let's say if this is 0 for any Y in X, then this is true if and only if the given vector or the given element X is 0. Well, the proof is quite straightforward. So for this direction, if X is 0, then taking the inner product of Y and X would give you a 0 inner product. And this is, of course, valid for any Y and X. And we know this already from the case of inner products. On the other hand, suppose that the condition or this condition is valid. By taking a specific Y, namely X, the given vector X, we have, so the inner product of itself is 0 by assumption, but this is nothing but the squared norm of X. Therefore, the norm of X is 0, and by positive definiteness of the norm, X must be 0. So indeed, this statement, this equivalence is valid. One can extend this in the case of the duality pairing. So if the duality pairing is valid for any X prime in the dual space of the Hilbert space X, then this is true if and only if X is 0. So for the proof, the basic idea is just to use the Riesz representation theorem. Take note that any element of the dual space of a Hilbert space can be written as an inner product with respect to some fixed vector and the previous equivalence. So once you have written the duality pairing as an inner product, you can apply this result here to establish this second statement. Now, our question here is that, is this valid in the case of Banach spaces? So if X is only a Banach space, can we say that this statement is also true when X is a Banach space? So if the value at a given point of the Banach space is 0, for any element in the dual space. Does this imply that x, the given vector x, is also 0? The answer is yes. For this implication, or I should say the reverse implication, can be established as follows. So if x is 0, then the duality pairing, by definition, this is nothing but the value of the linear function of x prime at x. So this is x prime of 0, and this is 0 by linearity. And this is valid for all x prime in the dual space. So that's the straightforward part. This one is the more so it requires more work to prove this, namely the Hahn-Banach theorem. And we will specialize in the case of real norm spaces as well. So to state the Hahn-Banach theorem, and to prove it, we need the Zorn's lemma. So before we state Zorn's lemma, we need to discuss some preliminaries. So let's start with defining what is a partially ordered set. So let's say that P be a set, and we have a relation so this is a subset of the Cartesian product. So suppose that this is a partial order. In other words, we have the following properties. So we have symmetry, or I should say reflexivity, meaning P is related to itself for any P in the set. Here I would like to emphasize that we write this. So P is related to itself if and only if the ordered pair PQ is an element of your partial order. So P is less or equal to Q. That's our notation for the partial order, if and only if the ordered pair is in the relation. So this partial order generalizes the less than or equal relation for real numbers. Next, this relation must be anti-symmetric. So if P and Q are in P, and P is less than or equal to Q, and Q is less than or equal to P, then P must be the same as Q. And finally, it must be transitive. So if P, Q, R are in P, P is related to Q and Q is related to R, then P must be related to R. In this way, the pairing or the pair is called a partially ordered set. Or sometimes it is called a Poe set. Further definition, so we say that a subset Q of P is called totally ordered if every pair is comparable. Every pair of elements in Q are comparable. That is, if for every P and Q in the subset, either P is related to Q or Q is related to P. So that is P and Q are said to be comparable. So one must be less than or equal to the other, or one must be related to the other. Next, an element M in the partially ordered set is called maximal if M is less than or equal to X, implies so for some X in P, this implies that M must be X. So if you think of the usual less than or equal in the case of real numbers, so if M is less or equal to X and M is maximal, then M must be the same as X. So in other words, there must be no element in P that is strictly larger than M. Finally, we say that P, or more precisely the partially ordered set, is inductive if every totally ordered subset, let's say Q, in P, has an upper bound. This means that one can find a U in P such that Q is less than or equal to U for any Q in capital Q. So U here is the upper bound for Q. So again, a subset of a partially ordered set is totally ordered if every pair of elements in that subset are comparable. An element of the partially ordered set is maximal if M is related to X for some X in P, then this would imply that M must be the same as X. And finally, a partially ordered set is inductive if every totally ordered subset of your post set has an upper bound. Based on this, we can now state Zorn's lemma. So this lemma states that any non-empty inductive partially ordered set has a maximal element. Well, it is known, but we will not prove this. It is well known in set theory that Zorn's lemma is equivalent to the action of choice. So roughly, the action of choice states that a non-empty collection of pairwise disjoint sets, there is a set which you can choose, wherein you can choose precisely one element in the sets of that collection. And as a result, it is also equivalent to the well ordering principle. So any non-empty set can be well ordered. In other words, that set has a total order for which every non-empty subset has a least element or has a greatest element. So here, the total order is an antisymmetric and transitive relation where any two elements are comparable. So again, the Zorn's lemma are equivalent under the ZFC set theory to the action of choice and the well ordering principle. So ZFC set theory refers to the set of actions for the Zermelo-Frankel plus the choice, the action of choice. So we will not discuss in detail this equivalence, but you may consult standard text in set theory for the proof of the equivalence for the action of choice with the Zorn's lemma, and as well as the well ordering principle. So let us now state the Hahn-Banach theorem for real vector spaces. So let's start with Hilbert space, or I should say a real vector space. And a Y, a subspace of X. And I have a sublinear form. This means that p of x plus y is less than or equal to p of x plus p of y for any xy in the vector space, and p alpha x is equal to alpha p of x for any x in your vector space and for any non-negative alpha. And finally, let us consider a linear form f defined on the subspace Y. Wherein this linear form is less or equal to P on the subspace Y. Then one can find an extension, say capital F, of this linear form, wherein this extension satisfies the same inequality at each point on X, and indeed this is an extension of your given linear form small f. In other words, the restriction of capital F on Y is F. So the Hahn-Banach theorem for real vector spaces states that, so if you have a linear form that is bounded from above by a sublinear form, you can extend the linear form on the subspace into the whole space, and still you retain the inequality. So let us look at the proof of this theorem. Of course, we may suppose that y is not equal to x. Otherwise, there's nothing to prove. So as a first step, according to this assumption, there exists an element, let's say x sub 0, that is in x but not in y. And then we define y naught to be y plus the span of x naught. So in other words, this is the following set. So y plus x naught, or alpha x naught, where y is in capital Y and alpha is scalar. So the main idea of the proof is the following. So suppose this is your subspace Y, and you have a vector not in Y. So what you do is you take the span of this linear span, this vector, and then you take the linear combination of the two. So at least in this illustration, the plane would be your y naught. So this would be y naught. Of course, extended indefinitely. So we have, let's say, a linear form defined on F. So we would like to extend this, okay, into a linear form in the whole space y naught. So to do this, let us introduce or define the following map. So you take an element in y naught, and we define this to be f of y plus alpha. Okay, so here we are now expecting linearity. So we need to have some constant c here. Okay. For some scalar c. To be chosen later. And here, of course, y is in capital Y and alpha is in R. Okay, so here we note that f naught is linear. So you take, let's say, two elements, y1 and y2 in Y, and you take three scalars, let's say alpha 1, alpha 2, and alpha in R. So you take the linear combination of the following. Alpha 2 x naught. So rearranging the terms inside the argument, you get the following. So here you have y2 plus alpha times alpha 1 . So alpha 1 should be only multiplied, or alpha should be only multiplied in y1 plus alpha 1 plus alpha 2 x naught. So by definition, this is f of alpha y1 plus y2 plus, so alpha 2c, okay. In fact, one can show that here the definition of f naught is or f naught is well defined. Okay. Now you apply the linearity of f. So we can pull out alpha f of y1 plus f of y2. And then we distribute here c. And for the first term, take note that this one is nothing but f of y1 plus alpha 1c. Okay, so the highlighted parts. And the second term for this and this is basically f of y2 plus alpha 2c. I should say f naught. And f naught as well in this case. Okay, so that proves a linearity of f naught. Moreover, the restriction of f naught in y is also equal to f. This follows from the fact that, okay, if I take y and capital Y, I can write this as f naught y plus 0 times x naught. And by definition, this is what? F of y plus 0 times c, which is equal to f of y. So therefore, f naught and f are the same on y. In other words, restricting f naught on y gives you the function f, small f. Okay, now the constant c here is still arbitrary. The role of c is the following. We choose c such that the inequality f naught less than p is satisfied on the larger subspace y naught. So this equation here, or this inequality here, or this statement here, is equivalent to the following. So f naught y plus alpha x naught is less than or equal to py plus alpha x naught for all y in capital Y and for all alpha in R. And in turn, this is equivalent to, okay, using the definition of f naught. Here. And putting this on the other side, we have the following. So alpha c is less than p of y plus alpha x naught minus f of y. So we choose c in such a way that this is valid. Let us label this as asterisk. So if let us consider a cases for alpha. When alpha is 0, okay, any c will do the job. Indeed, take note that p of y plus alpha x naught, so minus f of y, this is equal to, so if alpha is 0, this is the same as P of y minus f of y. Since P and f are the same on y, or I should say since P is greater or equal to f on y, this is positive. But this is also alpha times c, since alpha is 0. So here, any c will suffice. Case 2, what if alpha is positive? Then we can divide by alpha and rearrange the terms, or we can divide alpha and the inequality will be preserved. So here we have c. So this is equivalent to c divided by p of y over alpha plus x naught minus f of y over alpha. For the negative case, the inequality will be reversed. Okay, so this one is equivalent to c greater or equal to p of y alpha plus x naught minus f of y alpha. And we can rewrite this, okay, according to the linearity of f. Then we have here minus f p of negative 1 alpha minus x naught. Okay, there is some detail that we need to emphasize here, of course. So we need to what? Divide by negative alpha, I should say. So we have negative c. Because we already know that p is sublinear, so we need to divide by negative alpha, which is positive, okay? F of y, okay? So this is equivalent to, but first, let us write this as follows. So we can put this inside P since negative 1 over alpha is now positive, plus, and then applying linearity of f alpha. Or if we multiply a negative sign both sides, and then applying linearity of f, you have this minus p negative y alpha minus x naught. Okay. So here we need to be careful because p is only homogeneous with respect to a positive scalars. So what we do is we divide by negative alpha. Okay, so based on this discussion, take note that we need to choose C such that, okay, C is less than or equal to P times. So this is a generic element. Say this is W. And let's say this is Z, including the negative sign. So let's say this is Z and this is W. So based on this, we need to prove the following. So Z is less than P of Z x naught minus F of Z. So that's for the positive case, and for the negative case, we need to prove that this is greater or equal to F of W minus P of W minus X naught. So we need to choose C such that this is valid for any W and Z in the subspace Y. So here it is enough to prove that indeed this one is less than or equal to this in order to choose a number in between. Well, if they are equal, then you can take the common value. So indeed, such a C exists since, okay. So what we do is we take, let's say, the sum of FW and F of Z. We apply the linearity of F. We know that F is less than P on Y, and we know that, of course, W plus Z is in Y. So again, W and Z are elements of Y. And then the next task is to, okay, subtract and add. So we add, or first, yes, we subtract X naught, and we add X naught. Next, we apply the sublinearity of P. So P of the sum is less or equal to the sum of the P values. Okay, and now you see, after rearrangement, in other words, you put this on the left, you put this on the right, you have this inequality. So based on this, we know that, so we now know that this is less than or equal to this. So therefore, A and C in between these two numbers can be chosen. So that's the first step. So the first step is, okay, given a subspace Y, you take an element not in the subspace and you extend your linear function f into the larger subspace Y naught, and that extension is denoted by f naught in this proof. We have shown that indeed it is an extension since the restriction of f naught in Y is the small f. And moreover, this extension preserves the inequality for the given linear function f. So the one provided here. So by adding one vector in your subspace, that is not in your subspace at the first point, you can find an extension that satisfies the conclusion of the Hahn-Banach theorem. So ideally, you do this by roughly some sort of an induction. Okay. So you add vectors until you have the whole vector space X. And a more rigorous proof would apply the Zorn's lemma. So that would be our second step. Step 2. So we define a partial order. So this is, let P be the collection of all pairs, let's say Z G, such that Z is a subspace of X containing Y. Okay. And G is a map from Z to R that is linear the restriction of G on Y is F, small f, and G is less than or equal to P on Z. And we discuss also a partial order. So given two elements, let's say a Z1, G1, and Z2, G2 in this collection of pairs, Z1, G1 is related to Z2, G2 if and only if Z1 is a subset or equal to Z2 and G1 is the same as G2 on the smaller set. In other words, if you restrict the larger function on Z1, you get G1. Then you can show that, or it can be shown that this is indeed a partial ordered set. So next, we show that it is an inductive partial ordered set. So for that, let's start with a totally ordered set. Q. Okay. We show that this has, let's say, an upper bound. Okay. A candidate upper bound would be the following. So we define, let's say, Z star to be the union of all subspaces Z, wherein Z sub Z comma G is in P, I should say Q. Okay, so you take all subspaces in Q, and let us define G star from Z star to R as follows. So G star of Z is equal to G of Z if Z is in capital Z and the pair ZG is in Q. Okay, so first let us show that G star is well defined. Indeed, suppose that Z is in Z star. Then, according to the definition of Z star, there exists a pair Z1, G1 in Q such that Z is an element of the space Z1. Now, suppose I have another pair wherein Z is an element of Z2. Again, without loss of generality, let us suppose that Z1, G1 is less than or equal to. So first, let us consider the case where Z1, G1 is less or equal to Z2, G2. Then, according to this relation here, okay, Z1 is a subset of Z2, and G1 of Z1 is equal to G2 of Z, I should say Z, since we have this, or that is the way we have defined this relation. So the first must be a subset of the other, and you have G1 is the restriction of G2 in Z1. Okay, since Z is in Z1, then you have that. Okay. Similarly, if you have the other relation, then Z2 is a subset of Z1, and hence G2 evaluated at Z is the same as G1 evaluated at Z. In other words, G1 must be an extension of G2 in this case. These are the only two possible cases since a Q is totally ordered. Okay, so here you have two elements of Q. So they must be comparable. So one must be less than or equal to the other. So this means that G star is well defined since if you have, let's say, two sets, Z1 and Z2, containing small z, and z is the first component of a pair in Q, the function values, whether you use G1 or G2, are the same. Therefore, it is immaterial whether you choose G1 or G2. So roughly speaking here, we are making the subspaces larger and larger, and we will have an extension by simply pasting all the functions. So G is well defined. G star is well defined. So the linearity of G star follows from the linearity of G. The fact that the restriction of G star on Y is equal to F follows from the same property for G. And one can also show that G star satisfies this inequality because the G also satisfies the same inequality. In other words, this pair is an element of P. And furthermore, it is an upper bound of Q. This means that ZG is less or equal to Z star, G star for all ZG in Q. Well, this follows immediately because Z star is the union and G star is an extension of every G in this pair. So any totally ordered subset of P is bounded from above or has an upper bound. This implies that P is an inductive partially ordered set. It is clearly non-empty since you can take, let's say, Y. So let's note that Y and F is an element of P. So it's a non-empty inductive partially ordered set. Therefore, applying Zorn's lemma, P has a maximal element, let us say M and F. If M is not the same as X, then we can find a subspace M naught and a function F naught M naught into R such that the pair M naught F naught is in P. And also M is less or equal to M naught, F naught, and these two are not equal. According to step 1. So if these two are not equal, you take M as your subspace Y in step 1, and you take an element X naught in capital X that is not in the subspace, and you can find an extension. Of course, this is not possible. So this contradicts the maximality of MF. Thus, X is equal to M. Therefore, MF is equal to XF, and this is an element of P. And consequently, if we get all these properties, we have the following. So replacing Z by M or replacing Z by X, you have the following properties. So F is a mapping from M, or in other words, X to R. This is linear. The restriction in Y is F, and F is less or equal to P on Z or M or X. So here you just replace this by M or the case of X. Okay, so these properties, these three properties stated here, follows from the definition of your partial ordered set P. And this is what we would like to establish. So that's the Hahn-Banach theorem for real vector spaces. Now we add another structure, namely a norm on the vector space. And as a result, we can talk about the dual. So how can we, is it possible to extend a bounded linear functional on a subspace into the larger space? And this is the content of the following version of the Hahn-Banach theorem. So let's start with a norm space. A real norm space X and Y a subspace of X. And here we equip it with the norm of X. More precisely, the norm of y is the same as the norm of y in x. So if I have an element in the dual of the subspace y prime, then we can find an element in the dual space of the larger space X that is an extension of y prime. In other words, X prime restricted to y is y prime, and in fact they have the same dual norm. So in other words, a bounded linear functional on a subspace can be extended into the whole space, and the extension has the same dual norm with the given element y prime. So we will prove this using the Hahn-Banach theorem for real vector spaces. So let us introduce a map P from X to R as follows. So P of X is the norm of y prime and the norm of X for any X in capital X. Take note that this is a sublinear. In fact, this follows immediately from the homogeneity of the norm and the triangle inequality for the norm. So indeed, for any, let's say, xy in capital X, and for any positive or non-negative scalar alpha, P of X plus Y, so by definition, this is equal to the following product of norms, and then you just simply apply the triangle inequality, and then after distributing the norm of y prime, you get P of X plus P of Y. And also for a non-negative scalar, we can pull out the scalar. Since it is non-negative, we don't need to put the absolute value. And this is basically alpha P of X. So that proves the sublinearity of P. And take note that also the duality pairing, well, take note that this is nothing but the value of y with respect to the functional y prime. This is less than or equal to the product of the dual norm and the norm of y. Since the norm of y is the same as the norm of x, we can write the last expression in this way. But this is nothing but the definition of our sublinear form P. And this is true for any y in capital Y. In other words, y prime is less than or equal to p on y. Therefore, if we applying the Hahn-Banach theorem, for vector spaces, real vector spaces, with, of course, f being the functional y prime, okay, there exists a linear map f, but instead of capital F, we denote it by x prime. That is linear and x prime is less than p x, and this is an extension of y prime. So let us highlight this part. This is precisely what we need here. Okay. So it remains to establish this equality. Okay, so for an element of x having a unit norm, taking the duality pairing, this is, of course, equal to x prime of x. This is less or equal to p of x based on this inequality. And then we apply the definition of p of x. So this is the dual norm of y prime times the x norm or y norm of x. They're just the same. And since the norm of x is equal to 1, this is equal to just the norm of y prime. And similarly, take note that again, this is equal to, according to the linearity of x prime, we have this. And this is less, well, this would be greater or equal to negative p of negative x. So again, here you evaluate this at negative x and multiply by -1 both sides, and you have this. And by definition, this is negative the dual norm of y prime and the norm of negative x. But of course, this one, applying homogeneity, is also equal to 1. So this is equal to negative p of x. Or I should say this is equal to negative of the dual norm of y prime. Okay, so combining these two inequalities, we obtain that the absolute value of the duality pairing x prime and x is less or equal to, Okay, the dual norm of y prime. So taking the supremum over all x in x such that the norm is equal to 1. We have this estimate. However, this is according to the definition of the dual norm. This is the norm of x prime in capital X prime. So our goal is to show these two quantities. So we already have one inequality. Now, applying, let's say, the definition of the supremum. So note also that the dual norm of y prime is the sup of this. Okay, so given a positive epsilon from the definition of the supremum, I can find a y epsilon and y having y norm, which is the same as the x norm, equal to 1, and that the duality pairing is slightly larger. Is larger than a number is slightly smaller than the supremum. So we multiply it by, let's say, 1 minus epsilon. So this is the dual norm. Okay, take note that x prime and y prime coincides with y. So therefore, the left-hand side can be written as the duality pairing between x prime and y epsilon as well. Since according to the definition of the duality pairing, this is the sup over all this as long as the norm of y is equal to 1. So this one is greater or equal to x prime y epsilon. So therefore, we have this inequality. And now we can obtain the reverse inequality by passing epsilon to 0 from the right to obtain the dual norm of x prime is greater or equal to the dual norm of y prime. And this establishes the reverse inequality. Okay. And therefore, the norm of x prime is equal to the norm of y prime. Hence, we have extended y prime into x prime, having the same norm. So before we move to our question last time, so going back to our statement here. Before proving this direction, let us consider the following consequence of the Hahn-Banach theorem for real norm vector spaces. So let us consider X a Banach space. So we now have a completeness. Y a closed subspace that is not equal to X. Okay. And let us take an element, let's say X naught in X that is not in Y. Then it is possible to find or there exists an element in the dual space with norm equal to 1. So it is in the unit ball of the, or in the unit sphere of the dual space. And then this duality pairing is the same as distance between the point X naught and Y and the kernel of X prime is equal to Y. In other words, restricting X prime in Y gives you the 0 functional. So let us look at the proof of this theorem. So let us define a larger subspace Z, namely the direct sum of X and the linear span of X naught. Or I should say Y plus the direct sum of the linear span of X naught. And define Z prime from Z to R as follows. So what we do is we take a point in Z, so that is of the form Y plus alpha X naught. So Y is in capital Y and alpha is scalar. So let us define this to be alpha times the distance between X naught and Y. Okay, then we have the following observations. Z prime restricted to Y is 0 since, okay, for any Y in capital Y, Z prime of Y can be written as, of course, Z prime of Y plus 0 times X naught. So you can see that this is somewhat similar to the proof of the Hahn-Banach theorem. Also, Z prime of X naught, we can write this as Z prime 0 plus 1 times X naught. So we have here 1 times the distance of X naught and Y. And of course, we can neglect this portion here. Okay. So we also need to establish the linearity of Z prime. So for this, let us take two elements, y1 and y2 in capital Y, and three scalars, alpha 1, alpha 2, alpha in R. So proceeding as before, let us take the value of the following linear combination. So alpha times y1 plus alpha 1 x naught plus y2 plus alpha 2 x naught. Take note that these are the form of elements in Z. And we can write this as a Z prime alpha y1 plus y2 plus alpha 1 plus, I should say, alpha 1 plus alpha 2 x naught. Okay, so this is the same as, since this is an element of Y, this is the same as the distance, or alpha 1 plus alpha 2 times the distance of x naught and Y. And therefore, we can write this as alpha times alpha 1 and this is alpha times Z prime of y1 plus alpha 1 x naught plus alpha 2, or I should say Z prime y2 plus alpha 2 x naught. Take note that an element of Z can be written uniquely of this form, an element of Y plus some scalar multiple of x naught. Okay, so this proves linearity. On the other hand, for let's say for boundedness, so first, let us consider the case where alpha is equal to 0. So here, this is basically, by definition, equal to 0. Since you can write this as Z prime Y plus or you can use the fact that Z prime restricted to Y is 0. Okay. Now, if alpha is not equal to 0, then for all Y in capital Y, we can write this. Okay, so take note that this is equal to alpha, absolute value of alpha, times the distance of x naught and y. The distance being the infimum, so this is less or equal to x naught minus y So we take a particular element of y, namely this one. So we divide it by alpha so that applying homogeneity, that term will cancel. So this is now alpha x naught plus y. So the norm here is taken in x. Or of course, if you rearrange this, you have this. So therefore, for any z in capital Z, the norm of, or the magnitude of z prime z is less or equal to the magnitude of z in capital Z. Thus, z prime is an element of the dual space of capital Z, and the dual norm is less or equal to 1. Next, we show that indeed the norm is equal to 1. So again, we take a positive epsilon then we conclude that there exists a y epsilon greater than y such that x naught minus y epsilon, the norm of it is less than 1 plus epsilon times the distance of x naught and y. So we can find a distance that is less than a number that is slightly larger than the distance. Consequently, if we take, let's say, the dual norm of z prime, according to the definition, this is, well, greater or equal to z prime and then with a particular element of z, namely negative y epsilon plus x naught, divided by the norm of negative y epsilon plus x naught. By the way, here the norms of z, the norm of z is also the norm of x. So let us note that one. Okay, so take note that according to the definition of z prime, the numerator is basically, so here our scalar is 1, so that would be the distance of x naught and y divided by x naught minus y epsilon. Since the norm in z is the same as with x, okay, and then you apply homogeneity, you have this one. And based on the previous inequality, this one is greater or equal to 1 over 1 plus epsilon. Strictly greater than 1 plus 1 divided by 1 over epsilon. So again, if we let epsilon go to 0 from the right, so that we have this, okay, other inequality. So therefore, we can now conclude that z prime, the norm of z prime is equal to 1. So based on this, okay, we can now apply the rest to the Hahn-Banach theorem. And I will leave the details to you. So apply the Hahn-Banach theorem for norm spaces. So you can just take here y prime to be z prime and y equal to z in the previous theorem. And that will complete the proof of the corollary. And as a result, we now prove our claim. So suppose X is a Banach space. So given X in capital X, this duality pairing is 0 for all X prime in the dual, if and only if X is 0. So here we already established this implication due to a linearity. For this, we apply contra position. In other words, suppose X is not equal to 0. So we wish to establish the negation of this statement. In other words, it is possible to find an element in the dual space wherein when we evaluate it to 0, it is not equal to 0. Okay, now if we take Y to be the trivial subspace, okay, in the previous corollary, what we get is the existence. So that to exist, let's say, an X prime in the dual space, such that, okay, these properties are satisfied. So namely, so X prime of X, the duality pairing. As we said, this is the distance of x and y. So going back to the statement of the previous theorem or previous corollary, we use this, okay, with x not equal to x. Okay. This is of course not an element of y, since y is the trivial subspace and x is not 0. Okay, so the distance between x and y, of course, this is positive since x is not in y. In particular, the duality pairing is not equal to 0. So that's the negation of this statement. So we have established the contra positive. So therefore, our observation in the case of Hilbert spaces is also valid in the case of the Banach spaces. And that's it for the Hahn-Banach theorem. In the next lectures, we will discuss the dual spaces for more concrete function spaces, namely the Lebesgue spaces and the space of continuous functions. And that's it for this series of lectures. And see you on the next one.